Hi there. Today, we'll be diving deep into the CDN paper which was published way back in 2002 by Akamai. This is the original paper that laid the foundation of all the modern web as we know it today. This paper was the group of researchers from MIT actually founded Akamai in order to solve the flash crowd problem. So what initially happened was, as a sudden increase in traffic or a sudden spike in traffic was witnessed, most of the servers would actually go down since there wasn't a really feasible solution present yet before this paper that was able to handle the flash crowd problem. Flash crowd problem is nothing but just a sudden spike. Imagine there's a big Amazon's big Indian festival sale, and a lot of people tend to flock towards the website all of a sudden since the number of requests are significantly higher. What actually happened before was that the servers would not be able to handle all of these requests and they would crash down. And this was basically because a lot of the compute power was spent in dealing out or in transferring back the resources or assets to the end users. So CDNs and the CDNs solve this problem leveraging a very simple but radical concept. And now we will be discussing this in greater detail in the rest of this video. This is the white paper that laid the foundation of it all, and I will include a link to it down in the description below, so you might also download it and read it for yourself. Okay, so we'll get started with the content delivery networks, but before we get into what CDNs are, let's just try to understand why the need for one came about. Imagine you are a startup founder and you have started your application servers, you have started your startup, and in order to handle the less number of users, you only rely on a single server, a single EC2 instance in a certain region. For example, let's just go ahead with that analogy. So you are a startup founder, the number of requests, the number of users is significantly low, and the number of requests that are gotten to the server is quite low. Now your server is able to actually handle all of these requests. But now you are dealing with JSON data, text data, even assets such as PNG and video formats such as MP4, because this is an application and you have to deal with all of this data. One caveat to notice here is that JSON and TXT and other standard response formats actually take very less size and are transmitted almost instantly over the wire. But when you are dealing with assets such as PNG or MP4, these vary in size and their sizes can be as large as about, in case of videos, it might even be 500 megabytes. Who knows? Cool. And even if you are dealing out the images, that still would amount to a couple of megabytes at the very least. If you are actually using a compressed form, then that is reduced further. But for now, you need to take into consideration that since the number of users is relatively low, you do not see any performance hits when you're dishing out PNG, MP4, when you're sending these as responses directly from your application server. What happens if more number of users come now? Now your website has grown pretty popular, and now more number of users are requesting resources from your application server. Now your server is actually getting stressed out, is actually performing at a certain threshold above the load handling capability, and now you will need to actually scale it up. Either throw in more compute power, increase the memory, increase the RAM, everything, or you can actually come away cheap with having multiple application servers all at once and put a load balancer in front of them. So these application servers are identical to each other and connect to each other via shared state, that is, might be a shared database or something, but that is out of the scope of this discussion. But what I want to convey is that since one application server wasn't able to handle all of this particular request, you add in multiple servers, and in order to have them load balanced, in order to balance the load amongst them, you add a load balancer which delegates the request from the users to any particular application server depending on what amount of load each server has. You can do it in a round robin way, or you can actually monitor the actual load of the different servers. This particular concept, the last one, is actually used in Akamai quite a lot. So now you have created multiple application servers and put in a load balancer in front of them, and all the users will now request the resources, and they will be routed to the load balancer. The load balancer will then transfer these requests to each of the application servers in sequence, depending on the load factors again. So now, this is what we can refer to as a cluster. Many different computers come together, act together, and it gives the illusion of a single entity. This is what a cluster is, and this cluster will reside in a particular US East region, and you will be dependent on a single ISP or multiple ISP. In that case, it will be multi-homing. But let's just, for the sake of simplicity, go ahead with a single ISP for providing the network to your warehouse, not warehouse, to your data center, right? But as you could see, there's still a possibility of a single point of failure. What if the power supply to your cluster goes down? Or what if the ISP that you were relying on is also down? In that case, your service would not be accessible to any user. Now that is a problem. So what you do is, as you did before, you replicated multiple application servers so you would be able to better handle the load. And now you are faced with the availability issue, that is a single point of failure. Since if one cluster fails, everything goes down. Why not have two servers? Why not have two clusters? So that is what we are actually achieving as well. We create a replica of the original cluster in an entirely different region, and this is what we term as mirroring. So this is where mirrors come from. If you are a Linux enthusiast and you have to download packages, you must have come across the term mirrors. So now you know what exactly a mirror is, right? So if you have multiple clusters, you can also delegate the handling of the request based on the locality of the user. For example, since one of your cluster lies in the US region, you could actually route the request from a user in the US to a cluster in the US region itself. You do not have them to go over the internet and go across the continent to the Indian cluster, right? That doesn't make sense. So having multiple clusters means you can ensure that a particular set of users within that are near that cluster will be routed to that cluster itself. As a result of which, the latency gets reduced, the throughput improves, and your servers are better able to handle the request. Though you also would need to over-provision for the case where one of the clusters were to fail. Let's say that the US East cluster fails, and now all of these requests, in order to be available all the time, you would have to read out all of these requests to the Indian cluster. Now, you also need to make sure, that is where the over-provisioning comes in. You need to make sure that each of the cluster would be able to handle all of the traffic load of your service on its own. If not, this will also break down and your service would not be accessible to anyone, will not be available. Now you kind of get the idea that you almost always will have to over provision to handle such scenarios. You will have to invest more money upfront in infrastructure. You need to invest more money in maintenance of that infrastructure. Now, what if a single ISP, and now what if you rely on a single ISP and that goes down? You use multiple ISPs, so that is where the multi-homing concept comes in. Multi-homing actually comes with their own set of problems, which we'll discuss about later in the video as well. So, okay. Now, the crux of the problem is that, let's go back again to the initial problem that we had, is that your server was also dealing with handling out the PNGs and MP4s. You realized, okay, I am dealing out with these assets. Why not just cache them somewhere and I do not need to bother sending them out? Why not let that proxy thing handle it for me? That is another solution that was prevalent at the time, was using the proxy cache. Proxy cache is nothing but that is a cache within your ISP which stores the cacheable contents within its memory. That's it. That's pretty much what it is. So a user requests a particular content. Let's say he requests v1/img.png. The ISP, this request goes to the ISP. It checks whether this request corresponds to any that is present in the proxy cache. If it is, then we do not need to go to the origin server and just hand it out over here. So you can see one, you look into the cache and then you send back the data. If on the other hand there's a cache miss, what earlier happened was a cache hit. Now if there's a cache miss, you now need to go to the origin server, fetch the resource, store it in your cache, and then to give back to the user, so that the next time they request it, you can just give it directly from the proxy cache. There are multiple problems with this. First one is that even back in 2002, this approach didn't perform well, and the reason was that even at that time, the demand for dynamic content, the dynamic web, was increasing quite a lot, and due to this, the proxy cache were ineffective. We had a cache hit ratio of about 20 to 40% only. That is way back in 2002. Just imagine the state of the web right now. You can imagine this actually going down further and further. So proxy cache will only be able to store content that is casual, that is static in nature. You know they won't change, you know you will not be modified, there is no extra additional complexity that need to be addressed. So proxy cache would be better in that scenario, but the static web is no longer there. We always, almost always have a dynamic web, right? So as a result of which, this approach didn't pay any dividends. Also, our problem is that there is no control for content providers to cache the contents. Suppose that you want to cache image.png for 1 hour and you want to cache v2img2.png for, let's say, 3 hours. You cannot do that because the proxy cache has a TTL that is set of its own, independent of the consumers. The consumers don't have any say in the matter of how long the cached content should be. You cannot, moreover, ask the proxy cache, hey, to invalidate my entries. That is also not possible. And another problem that came about is since there are so many proxy cache across the world, we could come up with a standardization, but the ISPs were not able to come up with one, since you know the hassle of dealing with multiple people and coming to a conclusion. So in comes Akamai's CDN network. The main problem was we cannot rely on multiple ISPs for caching the contents in their local cache. That's it. So Akamai said, why not let's just own tons of edge servers and create our own network. That way we can ensure there is homogeneity in our network. We can dish out the proper infrastructure and the code to handle all of this. We can also provide custom features to enable the users to decide how they want to cache the content for. So Akamai CDN is nothing but what we discussed previous with the proxy cache. We have a globally distributed cache which delivers the contents to the user from the internet search that is nearest, that is the point that is nearest to the user geographically. Geographically, or you would actually say it is based on round trip time, but that is, again, that is an implementation detail. So you have multiple edge servers, which you also call point of presence or POPs, and now the user will request the service via the edge server instead of directly going to the origin server. Now, this change actually reduces a lot of burden from the origin server and delegates it out to the edge server. Remember when we started the discussion, we had to deal with the dishing out of PNGs, MP4s, or other asset types. Now that responsibility being freed, the origin server could instead focus on more computational heavy tasks or tasks that are actually more important to the application rather than dealing with transmitting out the resources. We have offloaded that burden to the edge servers, and these edge servers of points of presence, POP servers, would take on the responsibility of handling out these resources. So again, CDN is nothing but a globally distributed cache which transfers or delivers content to the user from the edge. Now, coming back to the point, instead of the user now going directly to the origin server, we make it so that they go through the edge server and to the origin server. How does this come about? That is where the beauty of DNS resolution and handling load balancing via DNS comes in. This is where the crux of the problem lies, or the crux of the solution lies, and this could be the key takeaway of how we can leverage this particular information, this particular design pattern into our own lives. Although this paper is quite a bit old, yet the learnings to be had here are significant. So let's dive deep into how we are accessing a website through CDN, how the configuration happens, what if the user goes and searches for the website, how they are routed via the edge server. Let's go ahead and explain it to you now. So first of all, you search in the www.example.com. You know DNS resolution happens. If you are not really sure how DNS resolution occurs, I will also upload a video explaining DNS resolution in greater detail. If you are watching this right now, you could also have a look at this particular video right up there, and you can get an in-depth idea on how DNS resolution actually works. But still, do not worry, I will be able to explain to you what actually happens behind the scenes right now. So when a user searches and hey, I want to search up www.example.com. Of course, computers don't know these human readable constructs. they know IP addresses. So we need some way to map the DNS names to the corresponding IP addresses. And this is what is termed as DNS resolution. And DNSs have killer nature. You have many domains, for example, .com, .example, and www. Www is entirely different, but you need to focus on example.com. So what we ultimately want is example.com should be converted into an IP address 1.2.3.4, and then we will be able to access or send our packets via the internet over to this IP address. Okay, so now we follow the standard procedure that is for the DNS resolution. We pass in the request to a DNS resolver. We query the root server for a .com TLD server. It gives us the IP address of the .com TLD server. We go to .com TLD server and ask for example.com's authoritative name server. So it returns out the IP address for the example.com authoritative name server, which actually contains, which is the authority and contains the actual IP address that we wish to make the request to. So now we go to the IP address of the authoritative name server, which is this, and ask, hey, can you give me the address of www.example.com? It says sure, but here's an alias instead. Go ahead and go to this alias. So we return back a www.example.com and append something else, that is the cdnprovider.com. This is what happens when we configure our service to work seamlessly with the DNS with the CDN. So they append in and provide an alias which will be now used in the further resolution process. So now this is returned back, and then we make another call to this www.example.com.cdnprovider.com, and then we again look for the .com TLD server. We get provider.com's IP address, and this is the CDN server. Let's say you are dealing with Akamai or you are dealing with CloudFront. All of these will have their own authoritative name servers, and then you make a request, hey, give me the IP address of this particular URL. www.example.com.cdnprovider.com. So now it goes ahead and looks into its mapping. It does mapping. What mapping is, let me just tell you. Mapping is nothing but just mapping a request to a particular server. That is all there is. So it looks into some key factors, which we'll discuss in greater detail now. It looks into some key factors and decides, okay, these are the edge servers which should be handling this request. So it gives the IP address of that particular server back to the resolver. It returns back, and now the user can make the call to the particular edge server and get the requested resource. So this is the entirety of how you access a website when a CDN has been configured. You use an extra step, that is the CNAME delegation. And with the help of this, you are able to get the resource from the nearest edge server. There are multiple factors, and this is the key part that does it all. This mapping should be able to handle the mapping of the request based on certain key criteria which are written here, which are nearness, availability, and likelihood. Nearness is basically the round trip time that the edge server would take with the user that is nearest to it, with the user that is requesting it. So based on the nearness. Availability is the edge server that I'm giving out to you is actually able to hold the load. What if it is already overburdened with too many requests? That is also what is determined by availability. Or what if the network is down? What is the network infrastructure monitoring tool? What is the network status right now? And again, we have third one is the likelihood. What is the likelihood that the edge server that I'm going to give it to you actually contains the data that you're requesting for? We almost always want a cache hit because that is optimally better, but we do not want to dish out edge servers always that have a cache miss. So we use consistent hashing for this. Again, explaining consistent hashing is beyond the scope of this video, but that will lengthen it too long. You can instead look at this video by Gaurav Sen over here, coming right up over here. And once you're done with that, you can return back. But let me just tell you in brief what consistent hashing does. So whenever you come across a request like v1/image.png, our sweet little example, you hash this value. You hash this request, and that hash will be computed and will look at what is the nearest server that would actually be able to handle this, that actually is mapped to this, and you now return the IP address of this particular server. That is what consistent hashing in a very nutshell. Of course, there are greater nuances to it. Again, you can look through the video. Okay, so this is how the entirety of the mapping occurs. Now, one key thing that I forgot to mention here is that how is the availability defined? How do they know that what all of the edge servers loads are at any moment of time and what the network infrastructure is like at any given moment of time? So they have built their own in-house monitoring system, which regularly takes updates from the edge servers of the load information and also does a trace out of the network infrastructure. And this information is conglomerated, is aggregated, and is regularly dished out to the mapper, to the lower level DNS. Basically, the mapper is nothing but a DNS, of course, a lower level DNS. So this DNS takes into account all of this information and then relays relays the IP address that is to be sent over the network. Now, we do not want single points of failure. What if the edge server that was authorized, that we returned back the IP address of, is not actually available? In that case, we will need to send multiple IP addresses. So usually the solution is that instead of sending just one IP address, we send multiple IP addresses. So even in case of even in case of the edge servers being failed, the client can always request the resource from the another server, another IP address. Another thing to note here is the TTL, is the level of the time to load parameter that is set for the different caching content. For the top level servers, it's almost about 1 hour, and for the bottom server, that is the lower level DNS server, it is only about 1 minute. So almost all of the request needs to come through the DNS, and they will be able to route out the information, route out the resources via the appropriate edge servers. Such a pretty neat little design, actually. Okay, so what are the different network services that are offered? Of course, you are offered static content. Static content is just, hey, here's this website. This is not going to change. Just keep it stored within you. Hey, here's an image. This is not going to change. Whenever someone requests, just give it out to them. Hey, there's this video. Just give it out to them. Simple. You do not need to make any modifications in order to handle it over. So that is what static content is. It is very simple to implement. You just have to store it in your particular cache. And if there's a cache hit, then of course, dish it out. If there's a cache miss, go to the origin server and get back the response, and then store it in your cache and then return back. Simple. We have the dynamic content. Dynamic content is basically a personalized feed. Let's say you are making your own Instagram account, your own Instagram application. You know that the layout of the app would almost be similar to each one of them, but the content in it needs to be filled as per the user that is requesting it. It should be personalized. So there is an additional complexity required in that you would have to generate the web page dynamically on the go depending on the user. So now this is a bit of a difficulty in how do you cache something like this. So what the Akamai white paper does is they break this entire application, this service, this component into different subcomponents, and they find out, okay, which of these are static in nature and which are actually dynamic in nature. So they cache the contents that are static, cool, and they request the resource that is dynamic in nature from the origin server. Once that is done, they assemble all of them together. Instead of requesting everything from the origin server and burdening it, we actually just request the required resource that is dynamic in nature and assemble it at the edge and deliver it out. This is what is actually happening in the edge server includes as well. This is a markdown. Edge server includes is nothing but a markdown methodology wherein we specify which of the resources are actually static in nature and the cache those, and the dynamic contents are requested over the wire from the origin server. Cool. I think that clears things up. And the final thing is it also is able to handle live streaming. Again, it demonstrates that availability is one of the key concerns when designing a distributed system. So what actually happens is whenever you are live streaming, the origin server would encode the request, and then continuously send out the stream to the entry point of the Akamai edge servers, Akamai CDNs. This entry point has the responsibility of providing this transcoded stream to all of the edge servers that will be able to handle out and give this result to the end users. Now, what happens again? This is the single point of failure. This could potentially be the single point of failure. So we always have a replica back here that is a slave, and it is always checking up on the entry point. And if at any point the entry point goes, and if any point the entry point server goes down, it assumes the IP address of it and starts to instead delegate the stream to the edge servers and so as to maintain seamless live streaming. Yeah, so that's pretty much what I wish to discuss. Particularly, this solution is quite beautiful, and there's a lot to be learned from how we can have DNS as the load balancer itself. No, so the next time you actually wish and you actually find that you have a bottleneck on dishing out the assets, let's look for a CDN. Although they are costly, but the dividends that could be had, the performance gains that could be had would actually be significantly better. So I think that concludes this video. I hope you liked it and you learned something from it. I highly recommend you to read back the paper as well. This was such a fascinating read, and this is one of the core papers that I think every software engineer should read for the learnings that could be had from this particular paper. So yeah, that's it, and I will see you guys in the next one.